77 million years ago, a small and unusual dinosaur walked across ancient North America, leaving behind clues that still puzzle scientists today. Its name was Troodon, and for many years it was known as one of the smartest dinosaurs ever discovered. That idea came from its large brain compared to its body, sharp eyesight, and hunting abilities. As new fossils were found and older discoveries were studied again, many ideas about Troodon began to change. But was Troodon a single dinosaur at all? For many years, the name Troodon was used for a small dinosaur that scientists believed lived during the late Cretaceous period. It became one of the best-known small dinosaurs because it was often described in books, museums, television programs, and classroom lessons. Many people learned that Troodon was a fast hunter with sharp senses and a large brain for its body size. As time passed, new fossil discoveries and careful studies changed the way scientists understood this animal. Today, the name Troodon is surrounded by uncertainty because the original fossils used to name it do not provide enough information to clearly identify the dinosaur that carried the name. The story of Troodon began during the 19th century, when scientists were discovering many dinosaur fossils across North America. Fossils from this time often consisted of only a few bones or even a single tooth. Early paleontologists had very limited material to study, and they sometimes named new animals from small fossil pieces because they believed the fossils had unique features. This happened with Troodon. The first fossil connected with the name was only a tooth. It was discovered in rocks that formed during the late Cretaceous, many millions of years before humans appeared. The fossil tooth was described in the year 1856 by the American scientist Joseph Leidy. He believed the tooth belonged to a type of lizard because its shape looked different from the large meat-eating dinosaur teeth known at that time. He created the name Troodon, which comes from Greek words meaning wounding tooth. The name was chosen because the tooth had large serrations that looked capable of cutting flesh. At that time, nobody knew that the tooth belonged to a dinosaur. As more fossils were discovered across western North America, scientists slowly realized that many small meat-eating dinosaurs existed alongside the giant dinosaurs that usually received the most attention. Some of these smaller dinosaurs had long legs, sharp claws, narrow jaws, and many pointed teeth. Fossils found during later years suggested that the animal connected with the name Troodon walked on two legs and hunted small animals. Even so, the original tooth remained the official fossil connected to the name, and this would later create a serious scientific problem. A single tooth can provide useful information, but it cannot always show exactly which dinosaur it belonged to. Many meat-eating dinosaurs had teeth that looked very similar. Teeth can also vary depending on the age of the animal or the position of the tooth inside the mouth. Because of this, identifying a dinosaur from only one tooth can be very difficult. During the 19th century, scientists did not have the large collections of fossils that exist today. They also had fewer methods for studying ancient animals. During the 20th century, many new fossils of small meat-eating dinosaurs were discovered in Canada and the United States. Some skeletons included skulls, arms, legs, tails, and feet. Scientists noticed that these dinosaurs shared many features with the animal they believed was Troodon. As a result, these fossils were often placed under the name Troodon, even though they were found far away from the original tooth. This practice continued for many years. Museums displayed skeletons labeled as Troodon. Children's books described its appearance. Television documentaries showed it hunting in forests and open plains. Artists created detailed pictures of its body, feathers, eyes, and movements. Many of these reconstructions were based on fossils that later studies suggested might belong to different dinosaurs instead of Troodon itself. The body usually connected with Troodon was relatively small. Adults were thought to reach a length of around 6 to 8 feet, although estimates changed depending on the fossil being studied. The body was lightweight. The legs were long and built for quick movement. The tail was stiff because of long supporting bones and tendons. This helped the animal keep its balance while running or making sudden turns. The head was narrow with large eyes that faced partly forward. This gave the dinosaur good depth perception. The jaws contained many sharp teeth with noticeable serrations. The neck was flexible, allowing the head to move quickly while searching for prey. Scientists believed the animal relied on careful observation while hunting. The arms were longer than those of many other small meat-eating dinosaurs. Each hand had 3 fingers ending in curved claws. These claws may have helped hold struggling prey. The hands could probably move with considerable flexibility, although scientists continue to study exactly how much movement was possible. The feet were unusual because the second toe carried a large curved claw. This feature is shared with other members of the group known as dromaeosaurs and their close relatives. Troodon and similar dinosaurs belong to another closely related group called troodontids. Their special toe claw was smaller than the famous sickle claw of animals such as Deinonychus and Velociraptor, but it was still an important feature. The teeth of Troodon-like dinosaurs attracted attention because they had large serrations and a distinctive shape. Scientists believed these teeth could slice through meat efficiently. Some researchers also suggested that the teeth may have allowed these animals to eat a wider variety of food than many other meat-eating dinosaurs. Small mammals, young dinosaurs, lizards, insects, birds, eggs, and other available food sources may all have been part of their diet. Evidence from fossilized stomach contents is very limited, so scientists cannot say exactly what Troodon regularly ate. Bite marks found on fossil bones sometimes suggest feeding activity by small meat-eating dinosaurs, but it is often difficult to identify the exact species responsible. Because of this, much of the information about its diet comes from studying its body structure and the environments where related fossils were discovered. One reason Troodon became famous was the belief that it possessed one of the largest brains relative to body size among known dinosaurs. Scientists estimated brain size by examining the inside of fossil skulls. They created models showing the space once occupied by the brain. These studies suggested that Troodon-like dinosaurs had larger brains than many other dinosaurs. This discovery led to many discussions about dinosaur intelligence. Some researchers suggested that Troodon may have been capable of solving problems better than many other dinosaurs. Others believed it had excellent vision, hearing, and coordination. These ideas attracted public interest because they challenged older beliefs that all dinosaurs were slow and unintelligent. One scientist named Dale Russell became especially well known for discussing what might happen if a dinosaur like Troodon continued evolving after the extinction event at the end of the Cretaceous period. He created a model showing a fictional intelligent descendant, sometimes called the Dinosauroid. This model had a large head, upright posture, and human-like body shape. It was never presented as a real fossil or prediction. Instead, it served as an idea for discussing evolution. Many people misunderstood it and believed scientists expected dinosaurs to eventually become human-like. That was never the scientific claim. As knowledge improved, many scientists questioned whether the fossils assigned to Troodon actually belonged to one species. Careful examination showed important differences among skeletons collected from different places. Some fossils came from Alberta in Canada, others came from Montana and several locations in the United States. Differences appeared in the skull, jaws, teeth, and other bones. These differences suggested that several closely related dinosaurs had been grouped under one name. If this was true, scientists needed to determine which fossils truly belonged to Troodon, and which represented different species or even different genera. The biggest challenge remained the original tooth described by Joseph Leidy. Since the official name Troodon was based only on that tooth, researchers had to decide whether the tooth contained enough unique features to identify the animal. Many experts concluded that it did not. Similar teeth appeared in several related dinosaurs. Without more complete fossils connected directly to the original specimen, nobody could confidently say which skeleton represented the real Troodon. This situation caused increasing concern because the name Troodon had become deeply established in scientific papers, museum displays, educational books, and public discussions. Changing such a familiar name would create confusion, but keeping it without clear evidence also created scientific problems. Modern paleontology places great importance on accurate naming. Each scientific name should be tied to fossils that clearly show the identity of the animal. If the original fossil cannot provide enough information, scientists may decide that the name is too uncertain for reliable use. Such names are called dubious names because they cannot be confidently connected to a known species. Many researchers now consider Troodon to be one of these uncertain names. This means the dinosaur that people once recognized as Troodon may actually represent one or more different animals. Some fossils formerly assigned to Troodon have been moved into other genera after detailed study. One important example is Laetinivernatrix. Fossils from Alberta that were once labelled as Troodon were carefully examined and found to have enough unique features to receive their own separate name. This showed that at least some skeletons previously identified as Troodon belong to a different dinosaur. Other fossils may also represent separate genera that lived in different regions or at different times during the late Cretaceous. Scientists continue studying these remains, searching for small differences that can separate one species from another. Small changes in skull bones, teeth, hips, legs, and feet can reveal important information about relationships among these dinosaurs. The uncertainty surrounding Troodon demonstrates how science changes when better evidence becomes available. Early scientists worked with very limited fossils. Later discoveries provided much more information. Modern technology allows researchers to create detailed digital models of fossils, study microscopic structures inside bones, examine growth patterns, and compare hundreds of specimens collected from different locations. These methods help improve accuracy even when long-accepted ideas must be revised. Although the name Troodon has become uncertain, the family known as Troodontidae remains well established. This family includes several small feathered dinosaurs discovered across North America and Asia. These animals shared many body features, including large brains relative to body size, slender bodies, long legs, grasping hands, and specialized teeth. Many troodontids lived during the Cretaceous period, although earlier members of the family also existed. Fossils from countries including China and Mongolia have greatly increased scientific understanding of these animals. Complete skeletons from Asia preserve details that are rarely seen in North American fossils, helping researchers understand how the group developed over time. These discoveries have also strengthened the evidence that many small meat-eating dinosaurs possessed feathers. Feather impressions preserved in fine sediment show that numerous close relatives of birds were covered with feathers used for insulation, display, nesting, and possibly limited gliding in some species. Even though direct feather impressions have not been found with the original Troodon fossil, most scientists think the animal traditionally called Troodon, during the late Cretaceous period, the animal that scientists have called Troodon lived in the western part of what is now North America. This period lasted from about 100 million years ago until about 66 million years ago, but Troodon itself lived during the later part of that time. Based on the fossil evidence that has been connected with this dinosaur over many years, it lived roughly between about 77 million years ago and about 76 million years ago, although many scientists now believe that some fossils once given the name Troodon may actually belong to several closely related dinosaurs. This has made the exact time range of Troodon more difficult to define, but the fossils still show that animals very much like Troodon lived during the final part of the late Cretaceous period. The late Cretaceous period was a time when the world looked very different from today. The continents were not in the same places they are now. Oceans covered large areas that are now dry land. Sea levels were much higher than today, and many regions that are now connected by land were separated by shallow seas. The climate was generally warm across much of the planet. There were no large ice sheets covering the polar regions. Forests spread across many areas, and different kinds of flowering plants became common. These changes created many places where dinosaurs and other animals could live. The western part of North America was divided by a large inland sea that stretched from the north to the south. This sea is known today as the Western Interior Seaway. It split the continent into two large land areas. The western land area is called Laramedia, while the eastern land area is called Appalachia. Troodon lived on Laramedia, which was a long strip of land between the inland sea on one side and the growing mountains on the other side. Laramedia was home to many kinds of dinosaurs. Large plant-eating dinosaurs walked across its forests and open spaces. Huge meat-eating dinosaurs hunted these animals. Smaller dinosaurs also lived there, filling many different roles in the environment. Troodon was one of these smaller dinosaurs. It shared its home with many other animals, including turtles, crocodiles, lizards, mammals, birds, flying reptiles, frogs, fish, insects, and countless kinds of plants. One of the best-known places connected with Troodon is the area that is now the Canadian province of Alberta. Many fossils believed to belong to Troodon or closely related animals have been discovered there. During the late Cretaceous period, Alberta did not look like it does today. Instead of cold winters and wide grasslands, much of the region contained forests, rivers, floodplains, ponds, and wetlands. Water flowed across the land through many river systems. Floods often changed the landscape, carrying sand and mud into low areas where the remains of plants and animals could later become buried. The rocks found in Alberta preserve an important record of life from the late Cretaceous period. Layers of rock formed slowly over long stretches of time as rivers carried sand, mud, and other materials across the land. When animals died, some of their bodies became buried before they could completely decay. Over millions of years, these buried remains slowly turned into fossils. Scientists study these fossils to learn about the animals that once lived there. Several famous rock formations in Alberta have produced fossils linked with Troodon. These formations include places where the remains of bones, teeth, eggs, and nests have been found. Teeth have been especially important because they are often preserved better than many other bones. For many years, isolated teeth were among the main pieces of evidence used to identify Troodon. Later studies showed that different kinds of small meat-eating dinosaurs had teeth that looked very similar. Because of this, scientists began to question whether every tooth once identified as Troodon truly belonged to the same animal. Even though there has been debate about which fossils belong to Troodon, there is little doubt that close relatives lived across the same general region during the late Cretaceous period. These dinosaurs were well suited to the forests and river valleys of western North America. They found food in many different places and probably moved through a variety of habitats while searching for prey. Another important area connected with Troodon is the American state of Montana. Fossils from Montana have also been linked with this dinosaur for many years. During the late Cretaceous period, Montana shared many of the same environmental features as nearby parts of Canada. Rivers crossed the land, forests covered large areas, and seasonal rainfall helped support rich plant life. These conditions allowed many different animal species to live together. The rocks in Montana contain fossils of famous dinosaurs, such as Tyrannosaurus, Triceratops, Edmontosaurus, Ankylosaurus, and many smaller animals. Troodon, or closely related dinosaurs, lived among these larger species. Because Troodon was much smaller than the largest meat-eating dinosaurs, it occupied a different place in the local food web. It hunted smaller animals instead of competing directly with the largest predators. Scientists have also reported fossils that may belong to Troodon or similar dinosaurs from other parts of western North America. These discoveries suggest that these animals were spread across a wide area rather than living in only one location. Different river systems, forests, and floodplains offered suitable places where they could survive. During the late Cretaceous period, the climate across Laramidia was generally warm. Temperatures changed from season to season, but conditions remained much milder than those found in many parts of the same region today. Rainfall supported forests filled with many plant species. Flowering plants became more common during this time, joining older groups such as ferns, conifers, and cycads. These plants supported large plant-eating dinosaurs, which in turn provided food for meat-eating dinosaurs. Troodon lived in places where rivers frequently changed their paths. Floods sometimes covered low areas with fresh layers of mud and sand. These events helped bury dead animals and preserved many fossils that scientists study today. Without these natural burial events, far fewer fossils would have survived for millions of years. The forests where Troodon lived contained many different tree species. Tall conifers stood above other plants in some areas. Flowering trees and shrubs spread through other parts of the landscape. Ferns covered damp ground, while mosses grew in moist places near streams and ponds. Fallen branches and thick plant cover created many hiding places for small animals. Small mammals lived among these plants. Most mammals during the late Cretaceous period remained much smaller than many modern mammals. They searched for insects, seeds, fruits, and other food. Troodon probably encountered these mammals while moving through the forest. Lizards, snakes, frogs, and countless insects also shared the same habitats. Birds became more common during the late Cretaceous period. Some birds flew through the forests, while others searched for food near rivers and lakes. Flying reptiles also remained part of the environment. Their wings carried them across rivers, wetlands, and open spaces as they searched for fish or other prey. The inland sea lying east of Laramidia strongly influenced the local climate. Large bodies of water often affect nearby weather by adding moisture to the air. This likely helped support forests and wetlands across parts of western North America. Storms may have brought heavy rainfall during some seasons, while other times of the year were drier. Troodon probably moved across different habitats instead of staying in only one small area. It may have searched along riverbanks, walked through forests, crossed open ground, and explored areas near ponds and streams while looking for food. Different habitats offer different hunting opportunities depending on the season and the animals available. Some fossil sites suggest that Troodon may have nested in open places where eggs could be protected, while receiving warmth from the environment. Fossil eggs and nesting grounds linked with troodontid dinosaurs have given scientists valuable information about their breeding behavior. Adult animals may have remained near the nests to protect developing eggs from predators. The late Cretaceous landscape changed over long periods as rivers shifted, floods reshaped valleys, and sediments slowly built up. Forests expanded into some areas while other places became wetlands or open floodplains. Troodon had to live within these changing environments throughout its lifetime. Many fossil discoveries come from rocks known as the Dinosaur Park Formation in Alberta. This formation preserves one of the richest collections of late Cretaceous animals anywhere in the world. Fossils from this formation have helped scientists understand the communities where Troodon and many other dinosaurs lived. The remains show that numerous species shared the same region at the same time. Scientists study not only bones but also pollen, leaves, wood, footprints, eggshells, and tiny fossils from ancient soils. These discoveries provide clues about the environment where Troodon lived. Fossil pollen reveals which plants were growing nearby. Ancient soils show whether the land was dry or wet. Fossil wood helps identify forests that once covered the region. The rivers flowing across Laramidia carried nutrients that supported many forms of life. Fish swam through these waters, while turtles rested along the banks. Crocodiles waited near the edges of rivers and ponds. Amphibians lived in damp places where water remained available for much of the year. The forests also contained many insects. Beetles, flies, dragonflies, ants, and other insects likely filled the air and covered plants. These small animals formed an important part of the food web. They provided food for birds, mammals, reptiles, amphibians, and possibly young Troodon individuals. As seasons changed, plant growth also changed. Fresh leaves appeared during warmer months, while seeds and fruits became available at different times of the year. These seasonal changes affected the movements of plant-eating animals, which also influenced the hunting opportunities for meat-eating dinosaurs such as Troodon. Scientists continue to examine fossils from Alberta, Montana, and nearby regions because new discoveries sometimes change earlier ideas. Bones once thought to belong to Troodon may later be identified as belonging to another closely related dinosaur. New fossils may also reveal species that were previously unknown. This careful work has shown that the family of dinosaurs related to Troodon was more diverse than once believed. Even with these changes in scientific understanding, the general picture remains clear. Troodon, or its very close relatives, lived across the western part of North America during the late Cretaceous period. They inhabited warm environments shaped by rivers, forests, wetlands, and floodplains. Their world contained a wide variety of plants and animals that formed rich and active ecosystems, where life continued through changing seasons and shifting landscapes. A Troodon began its life inside an egg that had been laid in a carefully chosen nesting place. Like many other meat-eating dinosaurs that lived during the late Cretaceous period, Troodon most likely reproduced by laying eggs rather than giving birth to live young. Scientists have learned about this part of its life by studying fossil nests, fossil eggs, and fossil embryos that have been linked to close relatives within the same group of small-feathered dinosaurs. Even though many details remain uncertain because the fossil record is incomplete, the available evidence provides useful information about how a young Troodon may have started life and slowly developed into an adult. The eggs were probably laid in nests built on the ground. A nesting place needed to provide some protection from flooding, strong winds, and animals searching for food. Adult Troodon may have selected slightly raised ground where water was less likely to collect after heavy rain. Small stones, loose soil, leaves, and other plant material may have formed part of the nest. Some nests may have been made by scratching shallow holes into the ground before the eggs were placed inside. This simple structure could help keep the eggs together, while allowing the parent to remain close during the long period before they hatched. The eggs themselves were probably long rather than perfectly round. Fossil eggs believed to belong to Troodon, or very close relatives, show that the eggs had hard shells, with tiny openings that allowed air to pass through. These openings were important because the growing young inside each egg needed oxygen while it developed. At the same time, the shell protected the embryo from damage, while allowing enough moisture to move through the surface. The shell also acted as a source of calcium, which helped the young dinosaur build strong bones before hatching. A female Troodon likely laid several eggs during one nesting period. Fossil nests linked to close relatives contain groups of eggs standing almost upright instead of lying flat. This arrangement may have helped the eggs fit closely together, while giving the parent enough space to sit above them. The eggs may have been partly buried in soil or nesting material, leaving only part of each shell exposed. This position could help keep the temperature more stable while still allowing enough air to reach the growing embryos. Scientists believe that one or both parents may have stayed near the nest for much of the incubation period. Fossil discoveries suggest that an adult sometimes remained directly above the eggs. This behavior may have helped protect the nest from hungry predators looking for an easy meal. Small meat-eating dinosaurs, mammals, lizards, snakes, and other animals living in the same environment could all have taken eggs whenever they found an opportunity. Staying close to the nest would increase the chances that more young survived until hatching. The parent probably had feathers covering much of its body. These feathers may have helped control the temperature around the eggs. The parent could adjust its position depending on the weather. During cooler conditions, it might settle more closely over the nest, while on warmer days, it could raise its body slightly to allow more air to move around the eggs. Small changes like these may have prevented the eggs from becoming too cold or too hot. Inside each egg, the embryo slowly formed over many weeks. At first, it was extremely small and depended entirely on nutrients stored inside the egg. The yolk provided fats, proteins, vitamins, and minerals needed for growth. As the embryo developed, tiny bones began to form. Muscles, organs, eyes, and other body parts gradually took shape. Feathers probably began developing before hatching, although they may have been short and soft instead of fully grown. The growing embryo also developed its jaws, teeth, legs, arms, and claws, while still inside the shell. Each new part formed according to instructions carried within its genetic material. As the bones became stronger, the embryo slowly filled more of the available space inside the egg. Near the end of development, movement became more difficult because the young dinosaur occupied almost the entire inside of the shell. Shortly before hatching, the young Troodon probably absorbed the last remaining nutrients from the yolk. This gave it an important supply of energy during its first days outside the egg. Like many living birds and reptiles, it may have developed a small temporary structure on its snout that helped crack the shell from the inside. Repeated pushing and twisting movements eventually created small breaks in the shell. After many efforts, the young dinosaur finally emerged into the outside world. A newly hatched Troodon was much smaller than a fully grown adult. Its bones were still developing, its muscles were not yet powerful, and its movements were likely less steady. Even so, it probably needed to become active very quickly. Remaining weak and helpless for a long time would increase the danger from predators. The hatchling may have rested for a short period after leaving the egg while its feathers dried and its body adjusted to the outside temperature. The young dinosaur was probably covered with a layer of soft feathers. These feathers helped reduce heat loss, which was especially important because a small body loses warmth faster than a large one. The feathers may also have helped protect the skin from sunlight, dirt, and small injuries. As the animal continued growing, these early feathers were gradually replaced by larger and stronger ones. Its eyes were probably already well developed when it hatched. Good vision would help the hatchling notice movement around the nest. Sharp eyesight could help it recognize its parents, locate food, and avoid danger. Troodon is known for having large eye sockets, suggesting that vision played an important role throughout its life, beginning at a very early age. The hatchling's hearing was also likely useful from the start. Sensitive hearing would allow it to notice calls from its parents and sounds made by approaching predators. Quick reactions could increase its chances of surviving during the dangerous first weeks of life. The brain of the young Troodon continued developing after hatching, allowing its senses and movement to become better as it matured. Food became one of the hatchling's greatest needs. Its growing body required large amounts of protein, minerals, and energy. Scientists are still uncertain whether the parents brought food directly to the young, or whether the hatchlings searched for much of their own food soon after hatching. Both possibilities are being studied because different groups of dinosaurs may have cared for their young in different ways. If parents provided food, they may have brought small insects, tiny reptiles, worms, or other easy-to-eat animals back to the nest. These food items would be small enough for the hatchlings to swallow without much difficulty. As the young dinosaurs became stronger, they could begin catching food on their own, while remaining close to the adults. If hatchlings searched independently, they probably stayed near the nest during their earliest days. Small insects crawling through leaves, tiny lizards hiding beneath plants, and other small animals would provide suitable meals. Learning to catch moving prey required practice. Many early attempts probably failed before the young Troodon became more skilled. Growth during the first months was likely rapid. Bones lengthened, muscles became stronger, and body weight steadily increased. Every successful meal supplied nutrients needed to build new tissue. The body constantly produced new bone cells, muscle fibers, skin cells, feathers, and blood. This continuous growth demanded a steady supply of food almost every day. As the skeleton expanded, the legs became longer and stronger. Troodon is believed to have been a fast runner, and this ability developed gradually during growth. At first, the hatchling may have stumbled while running across uneven ground. Over time, better balance and stronger muscles allowed smoother movement. Regular activity also strengthened the joints and improved coordination. The feet changed as growth continued. Strong toes helped support body weight while walking and running. Curved claws allowed the young dinosaur to grip the ground more effectively and possibly helped while catching small prey. These claws continued growing throughout life, with the outer covering wearing down through regular use and growing back as needed. The arms also became stronger with age. Feathered arms may have helped with balance while running, protecting the body, displaying to other Troodon, covering eggs later in life, or performing other behaviors that scientists continue to study. Although Troodon could not fly, Its feathered arms remained an important part of its body. The teeth changed throughout growth as well. Young teeth experienced wear from biting and holding food. Like many reptiles, Troodon probably replaced worn or damaged teeth with new ones during its lifetime. This process helped maintain effective feeding even after older teeth became dull or broken. The skull also continued changing shape as the animal matured. Bones slowly fused together and became stronger. The jaws gained more muscle, allowing stronger bites. The brain continued growing, supporting improved control of movement, better learning, and more effective use of the senses. Young Troodon likely became increasingly skilled at recognizing safe areas, remembering food sources, and responding to changes in its surroundings. As feathers matured, they probably became more organized and durable. Young feathers were replaced through natural cycles, ensuring that damaged feathers did not remain permanently. Healthy feathers helped maintain body temperature, protected the skin, and may also have played a role in communication with other members of the species. The exact color of Troodon feathers remains unknown because fossils rarely preserve enough evidence to determine their appearance with certainty. The young dinosaur gradually expanded the area it explored. During its earliest weeks, it probably remained close to the nesting site, but growing confidence and stronger legs allowed longer movements each day. It learned where food could be found, where water collected after rain, and which places offered shelter from larger predators. Every new experience added to its ability to survive in the changing environment of the late Cretaceous period. As the months passed, the difference between a hatchling and a juvenile Troodon became more noticeable. Its body became taller, heavier, and more powerful. Running speed increased, hunting ability improved, and its growing brain allowed more effective responses to the many challenges it faced each day. The size, body shape, and physical features of Troodon have interested scientists for many years, because this dinosaur is known mostly from scattered fossils, instead of complete skeletons. Even though the name Troodon has become famous, researchers have spent a long time trying to understand which fossils truly belong to this animal. Many fossils that were once called Troodon have now been placed into different dinosaur groups. Because of this, descriptions of its appearance continue to change as new discoveries are studied. Scientists now rely on the best available fossil evidence to build a clearer picture of what this dinosaur may have looked like during the late Cretaceous period. Troodon was not one of the largest dinosaurs that lived during its time. It was a relatively small meat-eating dinosaur with a light body built for active movement. Most scientific estimates suggest that it measured about 2 to 3 meters in length, although exact measurements remain uncertain because complete skeletons have not been found. Written in words, this means it was about 2 to 3 meters long from the tip of its snout to the end of its tail. It stood around 1 meter tall at the hips. Its weight has been estimated at roughly 30 to 50 kilograms, although different researchers have suggested slightly different values depending on which fossils they studied. Since the available remains come from different places and may even belong to different but closely related species, the exact size is still being studied. The body of Troodon was long and narrow rather than heavy. It had a slim build that helped reduce body weight. A lighter body would have allowed it to move quickly across the ground while using less energy than a much heavier dinosaur. The bones that have been found show that they were not extremely thick or heavy. Instead, many of the bones were slender, giving the animal a graceful appearance. Its head was one of its most noticeable features. The skull was fairly long, but not especially wide. The front part of the skull formed a narrow snout, This shape allowed space for rows of sharp teeth while keeping the head light enough to move quickly. Scientists believe the skull balanced well with the neck, making it easier for the animal to turn its head in different directions while searching for food or watching its surroundings. The eyes of Troodon were unusually large for a dinosaur of its size. The eye sockets found in fossil skulls show that the eyes occupied a significant part of the head. Large eyes usually collect more light than smaller ones. Because of this feature, some researchers have suggested that Troodon may have been active during low-light conditions such as early morning, late evening, or even at night. Other scientists believe the large eyes may simply have helped improve vision under many different lighting conditions. Since soft tissues do not become fossilized in most cases, the exact abilities of its eyesight cannot be known with complete certainty. The position of the eyes also provides useful information. The eyes faced somewhat forward instead of pointing entirely to the sides. This forward-facing arrangement created overlapping fields of vision. Such vision helps an animal judge distances more accurately. Better depth perception would have been useful when moving through forests, reaching for prey, or avoiding obstacles while running. The brain case of Troodon attracted much attention because it appeared relatively large when compared with the rest of the skull. This observation led some early researchers to suggest that Troodon may have had a larger brain relative to body size than many other dinosaurs. Scientists used casts of the inside of fossil skulls to estimate the shape and size of the brain. These casts showed areas where different parts of the brain were located. Although the actual brain itself was not preserved, the surrounding bone provided valuable clues about its possible size. The snout contained many small openings that allowed blood vessels and nerves to pass through the bones. These openings suggest that the snout may have been sensitive to touch. A sensitive snout could have helped detect movement, locate food hidden beneath leaves, or investigate objects found on the ground. However, the exact level of sensitivity remains uncertain because soft tissues are rarely preserved. Troodon possessed many small teeth instead of a few large ones. The teeth were sharp and had tiny serrations along their edges. These small tooth-like ridges helped slice food into smaller pieces. Unlike the large knife-like teeth of some giant predators, the teeth of Troodon were more delicate. They were suitable for gripping and cutting relatively small prey. One feature that made the teeth especially interesting was the unusually large number of teeth packed into the jaws. Scientists have counted many tooth sockets in fossil jawbones. This high tooth count allowed a long row of cutting surfaces inside the mouth. As old teeth wore out or broke, replacement teeth developed beneath them and eventually moved into place. Like many other dinosaurs, Troodon replaced its teeth throughout life. The lower jaw was slender and somewhat flexible. It was not built for delivering the powerful bite of much larger meat-eating dinosaurs. Instead, the jaw likely closed quickly while holding smaller animals securely. The muscles that operated the jaw were attached to areas at the back of the skull. Although these muscles were strong enough for feeding, they were probably not designed for crushing thick bones. The neck of Troodon was fairly long compared with the rest of the body. The neck bones showed that it could bend and turn with considerable freedom. This flexibility allowed the head to move in many directions without requiring the entire body to change position. Such movement would have been useful while searching for food, watching for danger, or interacting with members of its own species. The backbone extended from the neck through the body and into the long tail, each vertebra connected with the next to create a flexible but stable support system. Strong muscles attached along the spine helped control movement of the neck, body, and tail. The backbone also protected the spinal cord, which carried signals between the brain and the rest of the body. The chest was relatively narrow, the ribs curved around the body to protect important internal organs such as the heart and lungs. Although the exact shape of these organs cannot be known from fossils alone, the rib cage gives scientists an idea of the amount of space available inside the body. The shoulders supported the front limbs. Fossil bones show that the shoulder joints allowed a useful range of movement. The arms were longer than those of many meat-eating dinosaurs. Long arms provided greater reach when grabbing prey or handling objects. The shoulder blades rested along the sides of the rib cage and served as attachment points for muscles that powered the front limbs. Each arm ended in a hand with 3 fingers. The fingers were long and flexible. Sharp curved claws covered the ends of these fingers. These claws were useful for grasping prey, holding food, climbing over obstacles, or possibly digging through loose material. The bones of the fingers show several joints, allowing the hands to close around objects. The claws on the hands were not all the same size. Some were slightly larger than others, giving the hand different gripping abilities. The curved shape helped prevent prey from slipping away once caught. The claws were made of keratin in life, although only the inner bone usually survives as fossils. The wrists contained small bones that allowed controlled movement between the hand and forearm. Some researchers believe this flexibility helped the hands rotate inward to hold food more effectively. This feature is also important because similar wrist structures are seen in several close relatives of birds. The forearm consisted of 2 main bones. These bones worked together to support the muscles that controlled the hands and claws. Although the exact strength of the arms cannot be measured directly from fossils, the attachment areas on the bones suggest well-developed muscles. The hind legs were much longer than the arms. Long legs indicate that Troodon spent much of its time moving on 2 feet. Walking and running on the hind legs left the arms free for catching food or performing other activities. The leg bones were slender but strong enough to support the body during movement. The thigh bone connected the hip to the lower leg. Strong muscles attached to the upper part of the thigh, providing power for walking and running. Below the thigh, the shin bones formed the lower part of the leg. These bones were relatively long, another feature often associated with animals capable of moving quickly. The ankles were built to allow efficient forward movement. The arrangement of ankle bones provided stability while reducing unnecessary sideways motion. Stable ankles are important for maintaining balance during rapid movement across uneven ground. The feet contained 3 main weight-bearing toes that pointed forward. A smaller toe faced backward or remained raised above the ground, depending on posture. The forward-facing toes spread body weight across the foot while walking or running. Each toe ended in a sharp claw that provided grip on different types of ground. The second toe of each foot carried a larger curved claw than the others. This claw has attracted much scientific interest because it resembles the enlarged claws found in several related dinosaurs. The claw could be lifted off the ground while walking to reduce wear. During feeding or defense, muscles could raise or lower this claw as needed. Scientists continue to study exactly how it was used. Some believe it helped hold prey, while others suggest it played a role in climbing, defense, or interactions with other members of the same species. The enlarged claw was not as massive as those seen in some larger relatives, but it was still an important part of the foot. The bones inside the toe show special joints that allowed the claw to move through a wide range. Strong tendons attached to these bones helped control the movement. The hips supported the weight of the body and connected the hind limbs to the backbone. The hip bones formed a strong framework capable of handling the forces produced during running. Muscle attachment points on the hips indicate that the rear limbs contained powerful muscles. The pelvis was long and narrow. This shape allowed the hind limbs to move efficiently, while keeping the body balanced above the legs. The arrangement of bones also provided room for internal organs within the lower body. One of the most striking features of Troodon was its long tail. The tail made up a large portion of the animal's total body length. Many vertebrae extended through the tail, gradually becoming smaller toward the tip. Long tendons stiffened much of the tail while still allowing limited movement near the base. This partly stiff tail helped maintain balance when the animal changed direction during movement. The tail acted as an important balancing structure. As the body moved forward, the tail helped keep the center of mass over the hips. This balance allowed the hind legs to move efficiently, while reducing the chance of falling during sudden turns. Although the tail was relatively stiff along much of its length, it was not completely rigid. The first part of the tail near the hips retained greater flexibility. This flexibility allowed controlled adjustments during movement. The skin of Troodon is not well preserved in the fossil record. No complete skin impressions have been found that reveal every detail of its outer covering. However, scientists have discovered feathers in many closely related dinosaurs. Because of these discoveries, most researchers believe that Troodon was probably covered with feathers across much of its body. These feathers likely varied in size depending on the part of the body. Small feathers may have covered the face and neck, while longer feathers could have appeared along the arms, body, and tail. The exact arrangement remains uncertain because no complete feather impressions have been found directly attached to confirmed Troodon fossils. Feathers probably served several purposes. They may have helped keep body temperature stable by trapping warm air close to the skin. Feathers may also have played a role in communication between individuals. Different feather positions could have signaled excitement, warning, or readiness to mate. Since feather colors are rarely preserved, scientists cannot determine the exact appearance. The arms may have supported longer feathers that formed wing-like structures. These feathers were not necessarily used for powered flight. Instead, they may have assisted with balance while running, helped protect eggs during nesting, or played a role in displays. The tail probably carried rows of feathers as well. Tail feathers could have increased surface area without adding much weight. They may also have been useful during communication or courtship displays. The color of Troodon remains unknown. Fossils rarely preserve pigments. In a few feathered dinosaurs, scientists have identified tiny structures related to color, but similar evidence has not been confirmed for Troodon. Its body may have displayed shades of brown, gray, black, reddish colors, or combinations of several colors, but these remain scientific ideas rather than confirmed facts. The surface of the legs below the feathers may have been covered with scales similar to those seen on modern birds. Many feathered dinosaurs appear to have combined feathers on most of the body with scales on parts of the feet. This arrangement is considered likely for Troodon as well. The nostrils were positioned near the front of the snout. Air entered through these openings before reaching the lungs. Although the soft tissues inside the nose are not preserved, the surrounding bones suggest a well-developed nasal region. The ears of Troodon cannot be seen directly because the outer ear was made of soft tissue. However, openings in the skull reveal the location of the ear canals. The inner ear structure, preserved inside some fossil skulls, provides information about hearing and balance. Studies suggest that Troodon possessed good hearing abilities, allowing it to detect sounds produced by prey, predators, or members of its own species. The inner ear also played an important role in balance. Fluid moving inside the canals helped the brain detect changes in head position. Good balance was especially important for an animal that relied on two legs for movement. Scientists have also examined the sense of smell by studying parts of the skull connected with the olfactory system. Some evidence suggests that the sense of smell was reasonably developed, although it may not have been as dominant as vision. The mouth probably contained a tongue, although tongues rarely fossilize. The shape and movement of the tongue cannot be known with certainty. It likely helped position food before swallowing. The throat connected the mouth to the digestive system. Soft tissues from this region have not survived, but scientists understand its general function by studying living reptiles and birds. The digestive organs are not preserved in ordinary fossils. Even so, the body cavity provides clues about the available space for organs such as the stomach, liver, and intestines. These organs processed food and absorbed nutrients needed for growth and daily activity. The heart and lungs also remain unknown because they consisted of soft tissue. Their presence is understood from the needs of living animals and the space inside the rib cage. The bones of Troodon contain microscopic structures that reveal patterns of growth. By slicing thin sections of fossil bone and examining them under powerful microscopes, scientists can see growth rings and other features. These studies suggest that Troodon grew steadily throughout its younger years, before growth slowed as adulthood approached. Young individuals probably differed somewhat from adults. Hatchlings would have been much smaller and may have possessed proportionally larger eyes and shorter snouts. As they matured, the body gradually reached adult proportions. Male and female Troodon probably looked very similar in overall shape. Scientists have not identified clear skeletal differences that would easily separate the sexes. Minor differences may have existed in feather displays or body size, but current evidence is too limited to confirm this. The skeleton of Troodon contained many hollow spaces within certain bones. Hollow bones reduce body weight while maintaining strength. This feature is also found in birds and many related dinosaurs. Lighter bones make movement more efficient. Bone surfaces contain rough areas where muscles once attached. By studying these attachment points, scientists estimate the size and arrangement of muscles throughout the body. Although muscles themselves rarely fossilize, the bones preserve valuable evidence of their former presence. The joints connecting the bones were covered with cartilage during life. Cartilage rarely survives fossilization, meaning living animals were slightly larger than fossil skeletons alone might suggest. The thickness of cartilage also influenced how joints moved. The hands were capable of closing around objects rather than remaining permanently spread apart. Flexible fingers combined with curved claws created an effective grasping tool. This ability may have helped when catching small animals or handling food before eating. The neck muscles supported the relatively large head. These muscles attached to ridges and projections on the skull and vertebrae. Strong neck muscles allowed quick head movements while maintaining stability. The lower leg muscles attached through long tendons that reached into the feet. Long tendons improve movement efficiency by storing and releasing energy during walking and running. The chest muscles were important for controlling the front limbs. These muscles attached to the shoulder bones and upper arms, allowing coordinated movement during feeding and climbing over obstacles. The body center remained positioned above the hips because of the balance between the head, torso, and tail. This balanced arrangement reduced strain on the hind limbs during movement. Scientists often create computer models based on fossil skeletons to estimate posture and movement. These digital reconstructions suggest that Troodon usually carried its body nearly horizontal, with the tail extending behind it and the neck curving gently upward to support the head. The feet probably left three-toed tracks in soft ground. However, identifying footprints made specifically by Troodon remains difficult, because several similar dinosaurs produced tracks with nearly identical shapes. Some fossilized eggs and nests have been connected with close relatives of Troodon. These discoveries suggest adults may have crouched over nests while using feathered arms to cover eggs. Such behavior would have influenced the position and movement of the body during nesting. The claws required continuous growth because daily use caused gradual wear. Like modern birds and reptiles, the outer covering of the claws was made from keratin, which continued growing throughout life. Each tooth also developed continuously beneath older teeth. Replacement teeth formed inside the jaw before moving upward into position. This process ensured that worn or damaged teeth did not permanently reduce feeding ability. The vertebrae contained openings that reduced bone weight while maintaining strength. These openings also provided space for blood vessels and other tissues during life. The shoulder joint allowed the upper arm to move through several directions, although not every motion seen in modern mammals was possible. The exact range depended on the shape of the bones and surrounding muscles. The hip joint formed a strong connection between the thigh and pelvis. Smooth cartilage covered the ends of these bones, allowing movement with reduced friction. The tail muscles attached to the hips and upper leg bones. These muscles contributed not only to tail movement, but also to the power of the hind limbs during walking and running. The backbone contained many separate vertebrae connected by joints and supported by strong ligaments. These structures created a flexible column capable of supporting the body's weight while allowing movement. The rib cage expanded and contracted as the animal breathed. Muscles between the ribs likely assisted this movement, helping air flow into and out of the lungs. Scientists continue examining newly discovered fossils using modern technology, such as computed tomography scanning, high-resolution photography, and digital three-dimensional reconstruction. These methods reveal hidden details inside bones without damaging valuable specimens. Internal structures such as nerve passages, blood vessel channels, and air spaces become visible through these techniques. Every newly discovered fossil has the potential to improve scientific understanding of the size, body shape, and physical features of Troodon. Since complete skeletons remain extremely rare, each bone contributes additional information. Researchers carefully compare newly found fossils with older discoveries to determine which features truly belong to Troodon and which belong to other closely related dinosaurs. As scientific knowledge grows, descriptions of this dinosaur continue to become more accurate while remaining based on the available fossil evidence. Why Troodon was once called the smartest dinosaur became an important topic in dinosaur studies, because for many years this animal was widely described as having a higher level of intelligence than any other known dinosaur. This idea appeared in books, museums, television programs, magazines, classrooms, and documentaries. It shaped the public image of Troodon for many decades. Many people who learned about dinosaurs during the late 20th century remembered Troodon as the dinosaur with the biggest brain for its body size. Although later discoveries changed many parts of this idea, it is still important to understand why scientists first reached that conclusion and why the belief remained popular for such a long time. The story began with fossil discoveries that showed a small meat-eating dinosaur with features that seemed unusual. Troodon was not one of the largest dinosaurs. Instead, it had a light body, long legs, grasping hands, and large eyes. It also appeared to have a relatively large brain compared to many other dinosaurs known at the time. When paleontologists studied the skull, they noticed that the space inside the skull where the brain rested was larger than expected for an animal of its size. This attracted great attention because brain size has often been used as one way to estimate possible thinking ability in animals. Scientists cannot study the actual brain of Troodon because soft body parts almost never survive long enough to become fossils. Bones are much harder than brains and have a much better chance of remaining buried in rocks for millions of years. Since the brain itself was missing, researchers examined the inside of the skull. They created models of the empty space that once held the brain. These models are called endocasts. An endocast does not show every detail of a brain, but it provides useful information about its general size and shape. The endocasts suggested that Troodon had a brain that filled a larger part of its skull than many other dinosaurs that had already been studied. This finding encouraged scientists to estimate how large the brain was compared to the animal's body. When they made these estimates, Troodon ranked very high among known dinosaurs. This did not necessarily mean it was intelligent in the same way as modern humans, but it suggested that it may have had more advanced abilities than many other dinosaurs. Researchers often use a measurement called the brain-to-body ratio. This compares brain size with body size. A very large animal naturally needs a larger brain to control muscles, movement and body functions. Because of this, simply having a large brain does not automatically mean an animal is highly intelligent. A much better question is whether the brain is larger than expected for an animal of that size. Troodon appeared to have more brain tissue than expected for its body weight, making it stand out from many dinosaurs known during earlier studies. Another measurement that scientists sometimes use is called the encephalization quotient. This is a way of estimating whether an animal's brain is larger or smaller than expected for its body size. When Troodon was studied using this method, it received one of the highest estimated values among dinosaurs known at that time. These results strengthened the idea that Troodon had greater thinking abilities than many of its relatives. Its large eye sockets also played a role in this reputation. The skull showed openings for eyes that were unusually large for such a small dinosaur. Large eyes often suggest good vision. Scientists believed that Troodon probably depended heavily on sight while searching for food or watching for danger. Good vision requires important areas of the brain to process visual information. This supported the belief that Troodon possessed a more developed nervous system than many other dinosaurs. Some researchers believed that Troodon may have been active during the evening or at night. This idea came partly from studies of its eye structure. Large eyes can collect more light, making it easier to see under darker conditions. If Troodon hunted when light levels were lower, it would have needed strong eyesight and careful coordination. These possible abilities added to its growing reputation as a dinosaur with advanced senses. The ears of Troodon also attracted attention. Studies of its skull suggested that it may have had good hearing. Sharp hearing would have helped it detect small animals moving through plants or leaves. It also would have helped it notice approaching predators or members of its own species. Scientists believed that the parts of the brain connected with hearing may have been well developed. Its sense of balance may also have been highly developed. The inner ear helps animals control balance while moving. Fossil evidence suggested that Troodon may have been able to keep its balance well while running quickly or changing direction. This would have been useful for chasing prey or moving across uneven ground. Better balance requires close cooperation between the brain, eyes, ears, muscles and nerves. Troodon also had long legs built for speed. Fast movement alone does not prove intelligence, but quick animals often benefit from rapid processing of information. An animal moving at high speed must react quickly to changes around it. It must judge distance, avoid obstacles, and respond to moving prey. Scientists thought that Troodon may have had the brain power needed to perform these tasks effectively. Its hands were another feature that captured attention. Troodon had grasping hands with long fingers. These hands could probably hold prey more effectively than the simple forelimbs of many other dinosaurs. Some researchers suggested that the hands allowed more precise movements. Although this does not prove advanced thinking, animals with flexible hands sometimes perform more complicated actions while handling food or interacting with their surroundings. The claws on its hands were curved and sharp. These claws probably helped hold struggling prey. Troodon may have caught small reptiles, mammals, birds, insects, and other animals. Catching active prey requires careful timing and accurate movement. Scientists believed that this hunting style may have demanded greater coordination between the senses and the brain. Its teeth also seemed unusual. Troodon had many closely packed teeth with large serrations. These teeth were effective for cutting meat. Some paleontologists suggested that Troodon may have eaten a wide variety of foods instead of depending on only one food source. Animals with flexible diets sometimes show greater adaptability because they can take advantage of different opportunities when conditions change. Researchers also examined the overall body structure of Troodon. It was lightly built and probably moved quickly across the ground. Its long tail helped maintain balance while running. The skeleton suggested an active lifestyle rather than a slow-moving existence. Scientists believed that active animals often need efficient communication between the brain and the rest of the body. During the 20th century, many scientists compared Troodon with other dinosaurs, whose brains appeared much smaller in relation to body size. Giant plant-eating dinosaurs had enormous bodies but relatively small brains. Even many meat-eating dinosaurs had lower estimated brain-to-body ratios than Troodon. Because of these comparisons, Troodon quickly gained the nickname of the smartest dinosaur. The word smartest sometimes created confusion among the public. Many people imagined that Troodon had intelligence close to that of modern mammals or birds. Scientists were usually much more careful. They generally meant only that Troodon had one of the largest estimated brains relative to body size among dinosaurs known at the time. This is a much narrower statement than saying it possessed human-like thinking. Scientists have long understood that intelligence is difficult to measure. Brain size is only one part of the story. The structure of the brain also matters. Different brain regions perform different tasks. Some areas control movement, others process vision, hearing, smell, memory, or social behavior. Simply having a larger brain does not automatically produce higher intelligence. Another challenge is that fossils rarely preserve enough information to understand exactly how the brain functioned. Bones reveal shape and size, but they do not preserve thoughts, memories, emotions, or learning ability. As a result, every estimate about dinosaur intelligence contains some uncertainty. Even with these limits, Troodon remained one of the strongest examples available because its skull preserved enough information to allow detailed study. Researchers repeatedly examine new specimens using improved technology. As scientific methods improved, they created better digital models of the skull and brain cavity. During later years, computed tomography scanning became an important tool. These scans allowed scientists to look inside fossils without damaging them. Computer software created detailed three-dimensional models of the skull interior. These studies helped researchers estimate brain size more accurately than earlier methods. Some of these newer studies continue to support the idea that Troodon had a relatively large brain. Others showed that earlier estimates may have been somewhat too high because of improved measurements and better understanding of dinosaur anatomy. Even so, Troodon generally remained among the dinosaurs with higher estimated brain-to-body ratios. Another reason Troodon earned its reputation involved its close relationship with birds. Today, scientists know that birds are living dinosaurs. Troodon belonged to a group of dinosaurs that shared many features with the ancestors of modern birds. Birds are capable of learning, problem-solving, remembering locations, recognizing individuals, and communicating through many calls and displays. Because Troodon belonged to a branch close to bird ancestry, some scientists wondered whether it also possessed relatively advanced behavior. Its skull contained large openings for the eyes that faced somewhat forward. This arrangement may have provided improved depth perception. Depth perception helps animals judge distance accurately while reaching for objects or catching moving prey. Such visual abilities would have supported active hunting. Researchers also studied the size of the optic lobes, parts of the brain connected with vision. Although fossil evidence cannot reveal every detail, some studies suggested these areas were relatively well developed. Strong visual processing would have been valuable for tracking prey and avoiding danger. The possible hunting behavior of Troodon became another reason why people believed it was intelligent. It may have hunted small, quick animals that required careful observation and rapid decision-making. A hunter chasing active prey often benefits from accurate timing and flexible movement. Scientists also considered whether Troodon cared for its eggs. Fossil discoveries showed nests containing eggs believed to belong to troodontids, the group that included animals closely related to Troodon. Some fossils suggested that adults may have remained with their nests for extended periods. This behavior resembles brooding, where a parent protects or warms developing eggs. Parental care often requires more complex behavior than simply laying eggs and leaving them. Guarding nests involves recognizing danger, defending offspring, and remaining in one place for long periods. These possible behaviors contributed to the idea that Troodon may have possessed more advanced instincts than many other dinosaurs. Some nesting sites showed eggs arranged in organized patterns. The eggs were partly buried in the ground with pointed ends facing downward. This careful arrangement suggested deliberate nesting behavior rather than random egg-laying. Scientists viewed such an organization as another sign of behavioral complexity. Researchers also found evidence that Troodon may have taken time to choose nesting places carefully. A suitable nesting location would protect eggs from flooding, overheating, and predators. Choosing such places involves responding to environmental conditions rather than laying eggs without any apparent planning. The popularity of Troodon increased greatly through books written for children and adults. Many educational materials described it as the smartest dinosaur because this simple statement was easy to remember. Over time, the nickname became widely accepted outside scientific circles. Television documentaries often repeated the idea. Animated scenes showed Troodon carefully stalking prey, watching its surroundings and making quick decisions. While these scenes were based partly on scientific evidence, they also included educated guesses about behavior that fossils cannot directly prove. Museum displays frequently highlighted Troodon when discussing dinosaur brains. Visitors learned that most dinosaurs had relatively small brains compared to body size, while Troodon appeared different. These exhibits helped spread the image of Troodon as an unusually intelligent dinosaur. Artists also played an important role. Illustrations often showed Troodon with alert eyes, active body posture, and careful movements. These pictures influenced public imagination. Even though artists based their work on scientific evidence, artistic choices sometimes emphasized intelligence more strongly than the fossil evidence alone could confirm. During the late 20th century, one scientist even explored a highly speculative idea about what might have happened if Troodon descendants had survived until modern times. This proposal imagined an intelligent dinosaur evolving into a human-like form. The idea received public attention but was never accepted as scientific evidence. Most paleontologists viewed it as an interesting thought experiment rather than a realistic prediction. This speculation further strengthened the public image of Troodon as an exceptionally intelligent dinosaur. Many people came to believe that Troodon stood only a short distance away from human intelligence. Scientists generally rejected such claims because evolution does not move toward any fixed goal. Brain evolution follows many different paths depending on changing environments and survival needs. As more fossils were discovered, scientists gained a broader understanding of many dinosaur groups. They found additional species with relatively large brains, advanced senses, and bird-like features. These discoveries showed that Troodon was not entirely unique. Several closely related dinosaurs shared similar characteristics. Researchers also improved their understanding of bird evolution. Modern birds display a wide range of intelligence. Some birds solve puzzles, use tools, remember hundreds of food storage locations, recognize faces, and learn from experience. Since birds descended from certain dinosaurs, these abilities encourage scientists to think more carefully about dinosaur brains in general. This new understanding reduced the idea that Troodon alone represented dinosaur intelligence. Instead, scientists began viewing intelligence as something that probably existed in varying degrees across several different dinosaur groups. Troodon lived during the late Cretaceous period, at a time when many different kinds of dinosaurs, small mammals, reptiles, birds, insects and flowering plants shared the land. The places where it lived included forests, open woodlands, river valleys, floodplains, and areas with changing seasons. These different environments gave Troodon many opportunities to search for food, avoid danger, and find safe places to rest and raise its young. Its body was shaped in a way that allowed it to move across many kinds of ground without great difficulty. Every part of its body helped it travel through its surroundings while looking for food and staying alert to nearby animals. Troodon walked on two strong hind legs instead of moving on all four limbs. Its front limbs remained free while it traveled. This body plan allowed it to carry objects, hold struggling prey, scratch the ground, or perform other actions without slowing its movement. Walking on two legs also helped it keep its head higher above the ground, making it easier to watch for movement in the distance. A higher position gave its eyes a wider view of the surrounding land and helped it notice changes in its environment more quickly. Its hind legs were long in relation to the rest of its body. Long lower legs usually help an animal take longer steps while moving. Each step covered more ground than it would have with shorter legs. This meant Troodon could travel from one place to another while using less energy than if it needed many short steps. It could move through forests, along riverbanks, and across open ground, while searching for food throughout the day or during the evening. The muscles attached to its hips and upper legs gave power to each step. Strong muscles helped push the body forward while keeping it balanced. Every movement required the muscles, bones, joints, and tendons to work together. The bones supported the weight of the body, while the muscles provided the force needed for walking, running, turning, and stopping. This smooth cooperation between different parts of the body helped Troodon move with control instead of making sudden, unsteady movements. Its feet were built to support life as a fast-moving animal. Each foot had several toes that spread the body's weight across the ground. This reduced the chance of sinking into soft soil. The toes also helped keep balance while changing direction. Troodon probably walked across mud, dry earth, sandy ground, fallen leaves, and grassy areas during different seasons. A foot that could grip different surfaces made movement safer and more dependable. One of the best-known parts of Troodon's foot was the enlarged claw on the second toe. This claw curved sharply and could be lifted while walking. Lifting the claw helped protect its sharp edge from becoming worn down by constant contact with the ground. When needed, the claw could be lowered during hunting or defensive actions. Scientists continue to study exactly how this claw was used. It may have helped hold prey, grip surfaces, or defend against attacking animals. The tail of Troodon also played an important part in movement. It was long and stiff because of special structures inside the tail that limited side-to-side bending. A stiff tail acted as a balancing tool while the dinosaur walked or ran. When Troodon turned quickly, the tail helped keep the rest of the body steady. Good balance reduced the chance of falling while making sharp movements during hunting or while escaping danger. Balance became especially important when moving across uneven ground. Forest floors often contain roots, rocks, fallen branches, and patches of loose soil. Riverbanks can become slippery after heavy rain. Floodplains sometimes develop soft mud that changes from season to season. Troodon likely crossed all of these surfaces during its daily activities. Its body shape helped it remain steady while moving through places that were not flat or smooth. The neck of Troodon was flexible enough to allow the head to turn in different directions. Instead of turning its whole body every time it wanted to look around, it could move its neck and head first. This saved energy and allowed it to remain alert while standing still or moving slowly. Quick head movements also helped it follow the actions of small animals that might become food. Its large eyes probably gave it strong vision in lower light than many other dinosaurs. This has led many scientists to think Troodon may have been active during the early morning, late evening, or at night. If this was true, moving during these quieter times could have reduced encounters with some larger predators, while allowing it to search for active insects, small reptiles, mammals, and other prey. Light conditions changed throughout the day, and Troodon's eyesight may have allowed it to remain effective even when sunlight became weaker. Running required different movements than walking. During a run, the hind legs pushed against the ground with greater force. The body leaned slightly forward while the tail remained stretched behind to keep balance. Each step happened more quickly, allowing greater speed. The feet landed carefully before pushing off again for the next stride. Strong joints in the hips, knees, and ankles absorbed the force created by repeated impacts with the ground. Scientists cannot measure the exact running speed of Troodon because soft body tissues are not preserved in fossils. Fossil bones provide valuable information, but muscles, skin, and many other structures disappear long before fossils form. Researchers study the shapes of bones, the places where muscles attached, and the footprints left by related dinosaurs to estimate how quickly animals may have moved. These studies suggest that Troodon was probably a quick runner, capable of reaching useful speeds while hunting or escaping danger. Speed alone was not enough for survival. Control during movement also mattered. Troodon likely changed direction quickly, while chasing small prey that moved unpredictably. Small animals often make sudden turns while trying to escape. A hunter needed to react immediately without losing balance. Flexible joints, strong muscles, and a balancing tail all work together during these rapid changes in direction. Troodon probably spent much of its time searching for food instead of running continuously. Constant running uses large amounts of energy. Walking allowed it to cover greater distances while using less energy. It may have moved slowly while examining the ground, fallen logs, bushes and patches of vegetation where insects or small animals could hide. When prey appeared, it could quickly change from a slow walk to a faster chase. The changing seasons affected how Troodon moved through its environment. During warmer months, plants grew thickly, creating shaded areas beneath trees and bushes. Dense plant growth provided many hiding places for prey, but also made movement more difficult. Troodon needed to step carefully between branches and plants while staying alert for sudden movement. During cooler seasons, many plants may have lost their leaves, making the landscape more open. Different ground conditions required changes in movement throughout the year. Rainfall also changed the land. Heavy rain softened the soil and filled streams with more water. Wet ground became slippery, especially near rivers and lakes. Troodon may have slowed its pace while crossing muddy areas to avoid slipping. Dry seasons created harder ground that allowed quicker movement across open spaces. Dust, loose soil, and exposed rocks became more common when less rain fell. River valleys formed important parts of Troodon's habitat. Rivers attracted many kinds of animals because they provided water and supported plant growth. Small animals often gathered near these areas, creating feeding opportunities. Troodon likely travelled along riverbanks while searching for prey. It may have crossed shallow streams when necessary, choosing places where the water moved slowly and the ground beneath remained firm. Floodplains changed over time as rivers overflowed during certain seasons. Floodwater left behind fresh layers of mud and sand after returning to normal levels. These new surfaces sometimes preserved footprints made by dinosaurs and other animals. Fossil footprints discovered in different parts of the world help scientists understand how ancient animals moved across these changing landscapes. Troodon probably used different paths while travelling through its home area. Animals often learn routes that provide food, water, shelter, and safe resting places. Familiar paths reduce unnecessary effort and lower the chance of entering dangerous areas. Troodon may have remembered where food was commonly found and returned to successful hunting grounds many times. Its hearing likely helped guide movement as well. Sounds made by insects, birds, mammals, or other reptiles could reveal the location of prey. Listening carefully while standing still allowed Troodon to decide where to move next. It may have paused often, watching and listening before taking several more steps toward a possible food source. The sense of smell may also have played a part in daily movement. Odours carried by the wind can reveal nearby animals, decaying remains, fresh water, or nesting places. Troodon probably combined information from its eyes, ears and nose while exploring its surroundings. Using several senses together improved its ability to make safe decisions while travelling. Young Troodon almost certainly moved differently from fully grown adults. Newly hatched young were much smaller and weaker. They probably stayed close to the nest during the earliest part of life. As their legs became stronger, they slowly explored larger areas under the protection of adults if parental care occurred. Every week of growth increased muscle strength, coordination, and endurance, allowing young individuals to travel farther from their birthplace. As Troodon matured, its bones became stronger and better able to support longer journeys. Larger muscles developed through daily movement and hunting practice. Experience also improved movement. An older animal learned how to avoid dangerous ground, where prey often hid, and how to react when larger predators appeared nearby. daily experience shaped the way it used its environment. The environment itself contained many dangers. Large meat-eating dinosaurs lived in some of the same regions. Troodon needed to notice warning signs quickly. Fresh tracks, unusual sounds, or the smell of a predator may have caused it to leave an area immediately. Fast movement combined with sharp awareness increased its chances of survival. Rather than remaining in one place throughout the day, Troodon probably travelled across different parts of its home range. Food sources changed with time. Some insects appeared only during certain seasons. Small mammals moved to new nesting places. Reptiles searched for sunny or shaded locations depending on temperature. Troodon likely adjusted its daily travel based on where food could be found. Rest was also part of its daily routine. After spending time walking and hunting, it needed safe places where it could remain alert while recovering energy. Areas protected by vegetation or natural land features may have provided temporary resting sites. Even while resting, it probably remained watchful because predators could appear without warning. Wind influenced movement as well. Strong winds carried sounds and smells across greater distances. Troodon may have faced into the wind while searching for scents or listened carefully as changing air currents brought information from different directions. Wind also moved leaves and branches, creating background sounds that sometimes made detecting prey more difficult. Temperature affected activity. During very warm parts of the day, some animals reduce movement to avoid overheating. If Troodon followed this pattern, it may have become more active during cooler hours. Cooler temperatures allowed longer periods of walking and hunting without using as much energy to manage body heat. The structure of its skeleton suggests efficient movement over long periods. Every joint allowed specific kinds of motion, while limiting movements that might damage the body. The hips supported powerful leg muscles, the knees bent smoothly during each stride. The ankles helped absorb impact while allowing forward motion. Together, these features created steady and controlled travel across changing landscapes. Troodon shared its environment with many kinds of plants, including flowering plants, ferns, shrubs, and trees. Thick vegetation sometimes blocked direct routes. Instead of moving in straight lines all the time, it likely followed open spaces between plants. Animal paths created by repeated travel may also have offered easier movement through dense growth. Insects played an important role in the environment. Many insects lived beneath fallen logs, inside rotting wood, under leaves, and near water. Troodon probably explored these places while searching for food. Careful walking helped avoid making unnecessary noise that might scare away small prey before it could be caught. The ground itself constantly changed because of weather, growing plants, animal activity, and flowing water. Troodon needed to adjust its movements every day. Flexible behavior helped it deal with these changes instead of relying on only one pattern of travel. It responded to what it saw, heard, smelled, and felt beneath its feet while moving through forests, river valleys, open spaces, and floodplains. Using its long legs, balanced body, strong muscles, flexible neck, sharp senses, and careful movements to survive within the changing world of the late Cretaceous period. The sharp teeth of Troodon have been one of the most studied parts of its body ever since its fossils were first described. In fact, the name Troodon means wounding tooth, and that name came from the shape of one fossil tooth that scientists believed was very unusual, even though later studies showed that many of the first fossils belong to different animals, and that the history of Troodon is more complicated than people once thought. The teeth have continued to provide valuable information about how this dinosaur probably found food and survived. Teeth are often among the hardest parts of an animal's body. so they are more likely to become fossils than softer body parts. Because of this, many discoveries related to Troodon include teeth, and those teeth have helped scientists build ideas about its feeding habits. The teeth of Troodon were not shaped like the long, flat teeth of plant-eating dinosaurs. They also were not as huge or as thick as the teeth of giant meat-eating dinosaurs. Instead, they were small, narrow, sharp, and well suited for gripping flesh. Their edges had tiny saw-like points called serrations. These serrations acted like small cutting edges that helped slice through meat. The serrations on Troodon teeth were different from those found in many other meat-eating dinosaurs. Some scientists noticed that the serrations were larger and more widely spaced on certain edges of the teeth. This special pattern became one of the features used to recognize Troodon fossils. Each tooth curved slightly backward. This shape helped keep struggling prey from slipping away after being bitten. Once the teeth entered flesh, the backward curve made it harder for prey to escape. Many meat-eating dinosaurs had teeth with this general shape because it helped hold onto moving animals. Troodon also had many teeth packed closely together in its jaws. Having numerous sharp teeth increased the number of cutting edges available while biting food. The teeth were replaced throughout the dinosaur's life. Like many reptiles living today, Troodon did not keep the same teeth forever. As older teeth became worn, broken, or lost, new teeth slowly formed beneath them and eventually took their place. This natural replacement allowed Troodon to continue feeding without losing its ability to catch and eat prey. Tooth replacement was an important feature because hunting could damage teeth, especially when biting into bones, tough skin, or struggling animals. Scientists have carefully examined Troodon teeth under powerful microscopes. Tiny scratches and marks on the surface of fossil teeth can sometimes provide clues about diet. Different foods leave different patterns of wear. Meat, bones, insects, and plants may each create slightly different marks. Studies suggest that Troodon probably ate a wide variety of foods rather than depending on only one source. The sharp teeth show that meat formed an important part of its diet, but the overall shape of the teeth has also led some researchers to think it may have eaten smaller animals, insects, eggs, and perhaps other available foods whenever they could be found. The jaws of Troodon were long and lightly built. This jaw shape allowed the teeth to spread along a greater length, giving the animal many biting points. The muscles that closed the jaws were strong enough to grip prey, although they probably were not designed for crushing very large bones. Giant meat-eating dinosaurs developed massive jaw muscles capable of producing tremendous force, but Troodon followed a different feeding style. It likely depended more on quick bites, repeated attacks, and careful handling of prey than on overwhelming bite strength. The front part of the jaws carried sharp teeth that could grab prey quickly. Once an animal was caught, the remaining teeth farther back in the mouth could continue holding and cutting the food while it was swallowed in pieces. This arrangement would have helped Troodon manage prey that struggled during capture. Every tooth contributed to preventing escape. The skull itself played an important role in hunting. Troodon had a relatively light skull that reduced unnecessary weight. A lighter skull allowed quicker movements of the head. Fast head movements could improve accuracy while snapping at small animals. Small prey often reacts quickly, so the ability to move the head with speed may have increased hunting success. Scientists believe that Troodon probably hunted animals that matched its own body size or were smaller. Its teeth were well suited for catching small reptiles, mammals, young dinosaurs, amphibians, insects, and perhaps birds. During the late Cretaceous period, many small animals shared forests, river edges, floodplains, and other environments where Troodon lived. These places provided many opportunities to search for food throughout the day or night. The claws of Troodon were another important part of its hunting equipment. Each hand had 3 long fingers ending in curved claws. These fingers were flexible and capable of grasping objects. Flexible hands allowed Troodon to hold prey after catching it. Instead of relying only on its mouth, it could use both its jaws and its hands while feeding. The claws themselves were sharp enough to grip firmly, making escape more difficult for captured animals. The hands were attached to long arms that reached forward easily. This gave Troodon the ability to extend its claws toward prey before biting. The coordination between the eyes, arms, hands, and jaws may have made hunting more effective. Strong muscles in the shoulders and arms controlled these movements with precision. The claws on the fingers were not only useful for catching prey, they may also have helped while climbing over fallen trees, digging into nests, pulling apart food, or holding food steady while eating. Many modern animals use their hands or front limbs to secure food before taking bites, and scientists think Troodon may have behaved in similar practical ways without depending entirely on its mouth. The most famous claw of Troodon was located on the second toe of each foot. This claw was larger than the other toe claws and had a curved shape. It could be lifted slightly off the ground while walking, helping keep its sharp edge from wearing down too quickly. This special toe claw is found in many close relatives of Troodon and has attracted great interest among paleontologists. Scientists have proposed several possible uses for this enlarged toe claw. One idea is that it helped hold struggling prey against the ground. By pressing the claw into an animal while biting with the jaws, Troodon may have gained better control over its meal. Another possibility is that the claw helped during climbing, gripping uneven ground, or defending against attackers. Some researchers think it served several purposes instead of only one. The curved shape of the enlarged claw made it suitable for gripping rather than cutting through thick material. Although movies often show similar claws slicing open very large animals, fossil evidence does not strongly support such dramatic use. Instead, the claw likely functioned as a gripping tool that helped maintain control during close contact with prey. The feet of Troodon were built for movement. Long lower legs and narrow feet suggest that it could travel quickly across open ground. Speed is valuable for both hunting and avoiding danger. A fast predator can catch prey before it escapes, while a fast animal can also avoid becoming prey itself. Troodon probably depended on quick movement during much of its daily life. Balance was another important part of hunting. Troodon walked on its 2 hind legs, leaving the front limbs free for grasping. Its long tail acted as a balancing structure that helped keep the body steady while turning, stopping, or changing direction. Quick changes in direction would have been especially useful when chasing small animals that darted through plants or around obstacles. The body shape of Troodon suggests agility. Agile animals can react rapidly to changing situations. If prey suddenly changed direction, an agile hunter had a better chance of following it. Troodon's relatively light body would have supported these quick movements without carrying unnecessary weight. Its eyesight probably played a major role in hunting. Troodon had large eye sockets that suggest large eyes. Large eyes usually gather more light, making vision better in dim conditions. Some scientists think Troodon may have hunted during the evening, at night, or during the early morning when light levels were lower. Better vision under these conditions could have allowed it to find prey while avoiding larger predators that were active at different times. The position of the eyes also allowed overlapping fields of vision. This overlap improved depth perception, making it easier to judge distances accurately. good depth perception is valuable when reaching with claws or snapping at moving prey. Missing by even a small distance could allow prey to escape. The brain of Troodon was relatively large for a dinosaur of its size. Scientists believe this may have supported advanced senses, quicker reactions, and more flexible behavior. Successful hunting often depends on noticing small movements, remembering useful locations, adapting to changing conditions, and making quick decisions. A well-developed nervous system would have supported these abilities. The inner ear of Troodon has also attracted scientific attention. Fossils suggest that parts of the inner ear were developed in ways that may have helped maintain balance and coordinate head movements. Stable balance is especially useful when running quickly or focusing on moving prey. Hearing probably contributed to hunting as well. Although soft tissues rarely become fossils, the structure of the skull provides clues about hearing ability. Good hearing allows predators to detect rustling leaves, moving insects, or hidden animals before they become visible. Troodon may have relied on sound together with vision while searching for food. The sense of smell is more difficult to study because it depends partly on soft tissues that do not fossilize well. However, parts of the skull connected with smell suggest that Troodon likely possessed a useful sense of smell. Odors could have helped locate nests, injured animals, or carcasses left behind by other predators. Even if Troodon actively hunted much of its food, it may also have taken advantage of animals that had already died when safe opportunities appeared. Scientists often describe Troodon as an opportunistic feeder. This means it probably accepted different kinds of food depending on what was available. Sharp teeth and grasping claws gave it flexibility. If small mammals were present, it could hunt them. If insects were abundant, it could eat insects. If eggs were found in nests, it may have broken into nests and eaten them. If small reptiles or amphibians were nearby, they may also have become food. Young dinosaurs may sometimes have been vulnerable to Troodon. Hatchlings and very young individuals from other dinosaur species would have been much smaller than fully grown adults. A fast hunter with sharp teeth and grasping claws could have taken advantage of these young animals when the opportunity appeared. Eggs represented another possible food source. Dinosaur eggs contain nutrients and required less effort to capture than fully grown animals. Strong claws could have helped uncover nests hidden beneath soil or plants. Sharp teeth could then break open the shells. Whether Troodon regularly searched for nests remains uncertain, but many scientists consider it a reasonable possibility. Small mammals living during the late Cretaceous period were active in many habitats. These early mammals often hid among plants, burrows, and fallen logs. Catching such prey required patience, quick reactions, and careful observation. Troodon's body features suggest that it possessed many of these qualities. Insects may have been especially important during certain seasons. Large insects provided protein and were available in many environments. Troodon could probably snap them up quickly using its sharp teeth. Even though insects are much smaller than mammals or reptiles, eating many of them could still provide valuable nutrition. Small reptiles, such as lizards, may also have formed part of its diet. Lizards move rapidly and often hide among rocks, leaves, or tree roots. Flexible hands, sharp claws, and accurate vision would have been useful when catching such quick animals. Amphibians living near streams, ponds, and wetlands may also have become prey. Frogs and salamanders often gather around water, creating hunting opportunities. Troodon may have searched these wet places during certain times while exploring its environment. Some scientists have suggested that Troodon may occasionally have eaten fish if suitable opportunities appeared. Although its body was not specialized for swimming, fish trapped in shallow water or stranded along riverbanks could have been easy food. Opportunistic feeding allows animals to use whatever resources are available instead of depending entirely on one prey type. The process of hunting probably began with searching rather than chasing. Troodon may have walked slowly through its habitat while constantly looking and listening. Large eyes scanned the surroundings while sensitive hearing picked up small sounds. When movement was detected, it could quietly move closer before making a quick attack. Stealth may have played an important role during the final approach. Remaining unnoticed until the last moment increases the chances of catching prey. A smaller predator often benefits from getting close before attacking because long chases require more energy and give prey more opportunities to escape. Once prey came within reach, Troodon probably lunged forward using both its jaws and hands. Sharp teeth closed around the animal, while curved finger claws helped hold it in place. The enlarged toe claw may also have been pressed against struggling prey to reduce movement. If the prey escaped the first attempt, Troodon likely pursued it for a short distance. Long legs allowed quick acceleration across open spaces. Agile movement helped it follow sudden changes in direction. However, it probably did not depend on very long pursuits because prolonged chases consume large amounts of energy. Energy management is important for every predator. Hunting always carries the risk of failure, and failed hunts waste valuable energy. Troodon probably balanced active hunting with careful searching to reduce unnecessary effort. Waiting for the right opportunity often provides better results than chasing every possible target. The environment where Troodon lived contained many plants that created hiding places for both predators and prey. Ferns, shrubs, flowering plants, fallen trees, and uneven ground all affected hunting. Troodon had to move carefully through these habitats while remaining alert for sudden movement. Seasonal changes also influenced hunting opportunities. During nesting seasons, eggs and hatchlings became available. During wetter times, amphibians increased around water sources. Insect numbers may also have changed with weather and plant growth. Troodon likely adjusted its feeding behavior as food availability changed throughout the year. Young Troodon probably learned hunting gradually. Newly hatched individuals would not immediately possess the skills needed to catch active prey. Practice, experience, and physical growth likely improved hunting ability over time. Young animals may have begun by catching insects or other very small prey before progressing to larger animals. As Troodon matured, stronger muscles improved the power of its limbs and jaws. Larger body size also allowed it to tackle prey that younger individuals could not handle safely. Continuous tooth replacement ensured that sharp teeth remained available throughout these stages of growth. Injuries sometimes occurred during hunting. Prey animals defend themselves with teeth, claws, horns, kicks, or rapid movement. Even small prey can bite or scratch while struggling. Fossil evidence from many meat-eating dinosaurs shows that injuries were a normal part of life. Troodon likely experienced similar risks whenever it hunted active animals. Weather also influenced hunting success. Rain could soften the ground and affect movement. Wind could carry smells toward or away from the hunter. Darkness changed visibility. Troodon probably adjusted its activities according to changing environmental conditions. The sharp claws required regular use, but also protection from excessive wear. The enlarged toe claw remained lifted while walking, helping preserve its pointed shape. Keeping an important claw sharp would improve its usefulness whenever prey was captured. Scientists sometimes study living birds to better understand certain features of Troodon. because birds are living descendants of theropod dinosaurs. Many birds catch prey using quick movements, accurate vision, and coordinated feet and beaks. These observations provide ideas about how similar body structures may have functioned millions of years ago, although the exact behavior of Troodon could not be known with complete certainty. Fossil trackways made by related dinosaurs show that two-legged predators could move efficiently across different kinds of ground. Even though no trackway can prove exactly how Troodon hunted, footprints from similar animals help scientists understand walking speed, running ability, and body balance. The bones of Troodon show places where muscles attached. By studying these attachment points, researchers estimate the size and strength of different muscles. Strong muscles in the legs suggest effective running, while muscles in the arms supported grasping actions. Muscle reconstruction helps create a clearer picture of how the animal moved during hunting. Computer models have also been used to study Troodon. Scientists create digital versions of the skeleton and estimate how joints moved. These models test how far the arms could reach, how the neck turned, and how quickly the legs might have moved. Such studies continue to improve understanding of its hunting behavior. The neck of Troodon was flexible, allowing the head to move through many angles. A flexible neck made it easier to watch prey while keeping the body stable. It also helped position the mouth accurately during feeding. The sharp teeth remained the primary tools for cutting food after capture. Once prey stopped struggling, repeated bites separated flesh into pieces small enough to swallow. Troodon probably swallowed food without chewing in, the way mammals do today. Instead, the teeth mainly gripped and sliced rather than grinding food. Food passed into the digestive system, where strong stomach acids and digestive organs completed the breakdown process. Bones, skin, feathers, scales, and other materials may have been digested differently depending on their hardness. Some indigestible material may have passed through the digestive system without being completely broken down. The hunting abilities of Troodon resulted from many body parts working together rather than depending on only one feature. Sharp teeth secured prey, curved claws improved grip, flexible hands helped control struggling animals, long legs provided speed, balanced posture supported quick movement, large eyes improved vision, developed senses increased awareness, and a relatively advanced brain supported coordinated actions. Every feature added another part to the overall hunting strategy that allowed Troodon to survive within the environments of the late Cretaceous period. Fossils do not preserve the stomach contents of most Troodon specimens, so scientists cannot say with complete certainty what this animal ate during its lifetime. Even so, many clues found in its teeth, jaws, body shape, eyes, legs, feet, hands, and the places where its fossils have been discovered allow researchers to build a careful picture of its likely diet. Each new fossil and each new study adds more information, although some questions remain open because Troodon itself is known from fossils that have been debated for many years. Scientists study every small detail of the available evidence to understand how this dinosaur probably searched for food, what kinds of animals or plants it may have eaten, and how it survived in the environments where it lived during the late Cretaceous period. One of the strongest clues comes from the teeth. Troodon had many small teeth that were sharp and curved. The edges of these teeth had tiny serrations. These small cutting edges could help slice through flesh when catching and eating small animals. The teeth were not large enough for attacking huge prey, and they were also not shaped like the broad grinding teeth seen in plant-eating animals. Instead, the shape suggests that Troodon was suited for eating meat, although many scientists believe it probably did not eat only meat. Its teeth could have been useful for catching a wide variety of food that was available throughout the year. The jaws of Troodon were fairly narrow and carried many closely packed teeth. This arrangement allowed the animal to grip struggling prey. Small animals often move quickly and try to escape after being caught. A mouth filled with many sharp teeth would have made it harder for such prey to break free. Scientists think this would have helped Troodon feed on animals that could fit inside its mouth or could be torn into smaller pieces. The size of Troodon also gives clues about its diet. It was not one of the giant meat-eating dinosaurs of the late Cretaceous. Instead, it had a body that was much smaller, allowing it to hunt animals that larger predators might ignore. Small dinosaurs often filled important roles by feeding on insects, small reptiles, tiny mammals, young dinosaurs, birds, amphibians, eggs, and other small animals that were common in forests, river valleys, and open ground. Many researchers think insects were probably an important part of the diet. During the late Cretaceous, insects were found almost everywhere. Beetles, flies, dragonflies, termites, ants, and many other kinds lived among plants, fallen logs, streams, and patches of soil. A quick and active hunter like Troodon would have had many chances to catch insects during the day or at night. Large insects could provide useful amounts of food, especially when eaten regularly. The hands of Troodon were another helpful feature for finding food. It had long fingers that could bend around objects. These hands may have helped hold struggling prey after it was caught. They may also have been useful for moving leaves, breaking apart rotten wood, pulling aside branches, or reaching into small spaces where insects and other animals were hiding. Strong fingers would allow careful movements that could help search for food without wasting too much energy. Its long legs suggest that it could move quickly across the ground. Speed would help when chasing small animals that suddenly ran away. Quick movement would also help the animal travel between different feeding areas. Instead of waiting in one place all day, Troodon could likely search through many different parts of its environment until it found enough food. The large eyes of Troodon have attracted attention for many years. Some scientists have suggested that these eyes allowed it to see well in dim light. If this idea is correct, Troodon may have searched for food during the evening, at night, or in the early morning when many other animals were less active. Good vision in low light would make it easier to notice movement among leaves, bushes, or grasses. Small mammals, insects, reptiles, and young birds often become active during these quieter times of the day. Other researchers believe Troodon may have been active during both daylight and darkness, depending on weather, season, food supply, and danger from larger predators. Being able to search for food at different times would increase the number of feeding opportunities available throughout the year. The ears of Troodon may also have played an important part in hunting. Fossils of the skull suggest that hearing may have been well developed. Good hearing helps hunters detect small sounds made by moving animals. The rustling of leaves, the scratching of tiny feet, or the movement of insects through dry plants could all provide useful clues about hidden food. Animals that depend on careful listening often spend time stopping, watching, and listening before moving again. Troodon may have behaved in a similar way while searching through its surroundings. Its brain was relatively large for a dinosaur, leading many scientists to believe it could process information efficiently. Better awareness of its surroundings may have helped it remember good feeding places, recognize signs left by prey, and react quickly when an opportunity appeared. Finding food often requires paying attention to many small details, rather than simply running after every moving object. Scientists also think Troodon probably used its sense of sight together with hearing and smell. Although it is difficult to know exactly how strong its sense of smell was, Many meat-eating animals use several senses together while hunting. Smell can help detect hidden eggs, injured animals, dead animals, or prey hiding beneath plants. Even a moderate sense of smell would increase the chances of finding food. Eggs were probably one food source available to Troodon. Many dinosaurs, birds, and reptiles laid eggs during the late Cretaceous. Eggs contain large amounts of nutrients that support the growth of developing young. A hunter that found an unprotected nest could obtain an easy meal. Troodon had hands that may have helped pick up eggs or break open nests. Scientists cannot say how often this happened, but eggs likely formed part of the diet whenever they could be found. Young animals were another possible food source. Newly hatched dinosaurs, young birds, baby mammals, and small reptiles were easier to catch than fully grown adults. Their smaller size and limited experience made them more vulnerable to hunters. Troodon probably searched areas where young animals were likely to be present during nesting seasons. Small mammals had already appeared by the late Cretaceous. Most were active during the night and often searched for seeds, insects, or other food among plants. These mammals were usually fast and cautious, but Troodon may have been able to catch some of them by using patience, quick movement, and careful timing. Even catching a few mammals could provide valuable nutrition. Lizards and other small reptiles were probably common in many places where Troodon lived. These animals often rested on rocks, tree trunks, or warm ground before quickly running for shelter. A fast hunter with good eyesight and quick hands could have captured them before they escaped. Frogs and salamanders may also have been eaten. Wet areas near streams, ponds, and marshes supported many small amphibians. Troodon may have searched these places when conditions were suitable. Amphibians can be plentiful after rain, making them an attractive food source for hunters willing to visit damp habitats. Fish may also have been eaten when available. Shallow streams and ponds often contain fish that become trapped in small pools during dry periods. If Troodon walked near these areas, it might have caught fish close to the water's edge. Scientists cannot confirm that fish formed a major part of its diet, but the opportunity may have existed in certain environments. Carrion may also have been eaten from time to time. Dead animals provide food without requiring the effort and risk of hunting. Many meat-eating animals feed on fresh carcasses when they find them. Troodon may have done the same if it came across an animal that had recently died or had been left behind by a larger predator. This would allow it to gain nutrition while reducing the energy spent chasing prey. Plants may also have been eaten occasionally. Although Troodon is usually considered a meat-eater or an animal that ate many kinds of food, some researchers think it may have consumed fruits, seeds, or soft plant material when animal food was scarce. Eating different foods would help during seasons when certain prey became harder to find. Fossils alone cannot show exactly how often plant material was eaten, but many scientists consider this possibility reasonable. Seasonal changes likely affected food availability. During warmer parts of the year, insects, young animals, eggs, and other food sources may have been more abundant. During cooler periods, Troodon may have needed to search more widely or rely on different kinds of prey. Animals that can adjust their feeding habits often have better chances of surviving changing conditions. The environment where Troodon lived included forests, river systems, floodplains, and areas with many different plants. Each habitat supported different kinds of animals. Troodon may have moved between these places while searching for food. Forest floors contained insects, mammals, and reptiles. River edges offered amphibians and fish. Open areas allowed it to spot movement from a greater distance. By using many habitats, Troodon would increase its chances of finding enough to eat. Patience was probably an important part of hunting. Instead of constantly running, Troodon may have spent time quietly watching for movement. Sudden attacks often work better when prey does not notice the hunter. Remaining still before making a quick move could improve the chance of success. Quick reactions were also important. Small prey can escape within moments. Troodon likely depended on fast movements of its legs, neck, jaws, and hands to seize food before it disappeared into plants, burrows, or water. Every successful capture depended on careful timing. Searching for food probably occupied much of each day or night. Small hunters usually need frequent meals, because each individual prey item provides only a limited amount of energy. Instead of relying on one large meal, Troodon may have caught many smaller animals over extended periods of feeding. Scientists also examine fossil sites to understand what animals lived alongside Troodon. Fossils of insects, mammals, birds, reptiles, amphibians, fish, and many small dinosaurs have been discovered in late Cretaceous rocks. These discoveries help researchers identify the kinds of prey that were available in the same environments. Although they cannot prove exactly which species Troodon hunted, they provide a realistic picture of the food that could have been found nearby. Some scientists have suggested that Troodon may have remembered productive feeding areas and returned to them repeatedly. Places with abundant insects, nesting animals, or reliable water sources would continue attracting prey. Returning to such locations would reduce the time spent searching for food and increase the chances of successful hunting. The brain of Troodon has been one of the most discussed parts of its body for many years. Scientists became interested in its brain because the inside of its skull suggested that it had a brain that was larger than many other dinosaurs of its size. This discovery led to many studies and many ideas about how Troodon may have behaved, how it found food, how it stayed safe, and how it reacted to the world around it. Even though scientists have learned much more about dinosaurs over the years, the brain of Troodon continues to attract attention, because it provides clues about the way this animal may have lived during the late Cretaceous period. The name Troodon has also become more complicated as new discoveries have been made. Some fossils that were once placed under this name have later been moved to other closely related dinosaurs. Even with these changes, many of the fossils traditionally connected with Troodon have helped researchers study the shape of its skull and the space where its brain rested. The skull preserves important details that allow scientists to estimate the size and form of the brain, even though the brain itself did not become fossilized. Brains are made of soft tissue. Soft tissue usually decays long before fossilization can happen. Because of this, scientists almost never find the actual brains of dinosaurs. Instead, they study the inside of fossil skulls. Modern technology allows researchers to make detailed scans of the skull without damaging the fossil. These scans produce digital models of the empty space where the brain once sat. This space is called the brain cavity. By studying this cavity, scientists can estimate the size, shape, and arrangement of different parts of the brain. The brain cavity of Troodon appears to have been relatively large for a dinosaur of its body size. This finding led many researchers to suggest that Troodon had advanced thinking abilities compared with many other dinosaurs known at the time. It is important to remember that a larger brain does not automatically mean an animal was highly intelligent in the same way as humans. Intelligence includes many different abilities, and these cannot be measured simply by brain size. Even so, brain size can provide useful information about how an animal processed information from its surroundings. Scientists often estimate the relationship between brain size and body size by using measurements from fossil bones and skulls. These estimates suggest that Troodon devoted a greater amount of its body resources to its brain than many other dinosaurs. This may have helped it process sounds, sights, smells and movements more effectively. A brain that can process information quickly may help an animal notice danger, locate food, and react to changing conditions. The front part of the brain is often linked with learning, planning movement, and processing information from the senses. Studies of the skull suggest that this part of the brain may have been fairly well developed in Troodon. This does not mean that Troodon solved difficult problems in the way humans do. It simply means that it may have been able to handle information from its surroundings in a more detailed way than many other dinosaurs whose brain cavities appear smaller. The middle regions of the brain were connected with receiving information from the eyes, ears, and other sensory organs. These parts helped the animal understand what was happening around it. Every movement in the surrounding environment created information that traveled through the nervous system to the brain. The brain then decided how the body should respond. If something moved suddenly, the brain could send signals to the muscles to change direction or prepare to escape. The back part of the brain helped control balance and body movement. Walking, running, turning, and keeping the head steady all depended on communication between the brain and the rest of the nervous system. Troodon had long legs, a long tail, and arms that needed careful coordination during movement. The brain helped keep all these body parts working together. The cerebellum is an important part of the brain in many animals. It helps control smooth movement and balance. Scientists believe this area may have been well developed in Troodon, because it likely needed careful control while moving across uneven ground. Small adjustments made by the muscles allowed the animal to stay balanced while walking, running, or changing direction. The spinal cord carried messages between the brain and the body. Nerves branching from the spinal cord reached the legs, arms, neck, tail, and internal organs. Whenever Troodon sensed something through its eyes, ears, nose, or skin, the information traveled along nerves until it reached the brain. The brain then sent new signals back through the spinal cord to the muscles that needed to respond. The senses played an important role in the daily life of Troodon. Every living animal depends on information gathered from the environment. Food, water, shelter, mates, rivals, and predators all had to be detected before the animal could react. Troodon probably relied on several senses working together rather than depending entirely on one. Vision has received more attention than almost any other sense in studies of Troodon. The skull contains very large eye sockets. These openings held the eyes during life. Large eye sockets usually indicate relatively large eyes. Large eyes allow more light to enter, making it easier to see when light levels are low. Because of this feature, many scientists have suggested that Troodon may have been active during the evening, early morning, or even at night. Other researchers believe it could also have been active during the day depending on food availability and environmental conditions. Large eyes collect more light than small eyes. Light enters through the front of the eye and passes through the pupil. The amount of light entering the eye changes depending on the size of the pupil. After entering the eye, the light reaches the retina, where special cells respond to it. These cells send electrical signals through the optic nerve to the brain. The brain then creates the image that the animal sees. The position of the eyes on the front part of the skull suggests that Troodon probably had good forward vision. When both eyes look toward the same area, the brain receives information from each eye at the same time. This allows better judgment of distance. Knowing the distance to an object helps an animal move safely, avoid obstacles, and approach food with greater accuracy. Depth perception would have been useful while moving through areas filled with plants, fallen branches, rocks, and uneven ground. It would also have helped Troodon judge how far away small animals were before attempting to catch them. Accurate distance judgment reduces wasted effort and helps an animal move more efficiently. The optic nerve connected each eye directly to the brain. This nerve carried large amounts of visual information every moment that the eyes were open. The brain needed enough processing ability to understand this information quickly. A delay in processing could reduce the chance of catching food or avoiding danger. Scientists sometimes study the optic lobes inside the brain cavity. These areas are involved in processing visual information. Fossil evidence suggests that vision was an important sense for Troodon. The brain appears to have devoted a considerable amount of space to handling information received from the eyes. Movement attracts attention in many animals. A small animal running through leaves or grass creates changing patterns of light and shadow. Eyes that are good at detecting movement allow an animal to notice these changes quickly. Troodon may have been especially alert to movement because small prey often move suddenly and unpredictably. The shape of the skull also influences vision. The bones surrounding the eyes protected them, while still allowing a broad field of view. Strong bones around the eye sockets reduce the chance of injury during everyday activity. Since eyesight was probably very important, protecting the eyes would have been valuable for survival. The surface of the eye was likely covered by a clear layer that helped protect it while allowing light to pass through. Tears or similar fluids probably kept the surface moist and removed small particles of dust or dirt. This protective system is common among living land animals and helps maintain clear vision. Blinking also helps protect the eyes in many living animals. Although soft tissues do not fossilize well, Troodon almost certainly possessed eyelids that closed over the eyes. These eyelids protected the eyes from injury and prevented them from drying out. Some modern birds possess an extra transparent eyelid called the nictitating membrane. This thin layer can move across the eye while still allowing vision. Since birds are living relatives of dinosaurs, some researchers have suggested that Troodon may also have possessed a similar structure, although direct fossil evidence has not been found. Color vision depends on special cells in the retina called cones. Another type of cell called rods is more sensitive in dim light. Fossils cannot reveal exactly how many rods or cones Troodon possessed, because these soft tissues are not preserved. Scientists therefore study living birds and reptiles to make informed estimates. If Troodon had many rod cells, it may have seen well in low light. If it had many cone cells, it may have recognized a wider range of colors. It is also possible that it possessed a balance of both types, allowing useful vision under different lighting conditions. The eyes and brain work together continuously. Every change in brightness, movement, shape, and direction produced information that traveled to the brain. The brain organized these signals almost instantly. This allowed Troodon to react to its surroundings without needing long delays before moving its body. The pupils probably changed size depending on the amount of available light. During bright daylight, smaller pupils would reduce the amount of light entering the eyes. During dim conditions, larger pupils would allow more light to enter. This adjustment helped maintain clearer vision under changing environmental conditions. The muscles surrounding each eye allowed it to move in different directions. Looking upward, downward, or sideways helped Troodon inspect its surroundings without moving its entire head every moment. Head movement and eye movement together created a wider awareness of nearby activity. The neck also contributed to vision. Troodon had a flexible neck that allowed the head to turn toward interesting sights or sounds. Combining eye movement with head movement increased the area that could be observed while standing still. This reduced unnecessary body movement that might attract the attention of prey or larger predators. The brain constantly combines information from the eyes with information arriving from the ears, nose, skin, muscles, and joints. Each source of information helped create a more complete understanding of the environment. When several senses confirmed the same event, the brain could respond with greater confidence and speed.